All right, in today's lecture, we're going to discuss the first part of the section 4.3 material on separable equations. So let's start by defining what exactly a separable equation is. So here it is. A separable differential equation is any first-order differential equation, so that it means it only involves the first derivative, which can be expressed in the following form. The form dy dx, so the derivative of y, is equal to the product of a function of x and a function of y. So this terminology, separable, is referring to the fact that our derivative, or the right-hand side of this equation, can be factored as the product of a function of x and a function of y. Now, these types of differential equations are among the easiest to solve. And the idea in solving a separable differential equation is that we're going to try to separate our variables. So in general, x and y, sometimes maybe y and t, or x and t, just depending on the notation of the problem, and then integrate both sides. So to illustrate the general process for solving a separable equation, let's consider this general form for a separable equation. Something of the form dy dx is a function of x times a function of y. So my first step in solving is going to be to try to separate the variables. So I mean that I want to get everything involving x on one side of my equation and everything involving y on the other side of my equation. So in this general case, I could maybe start by multiplying both sides by dx, and I would have dy is f of x times g of y dx. And now if I wanted to get all of the variables y on one side of my equation, I could divide both sides by g of y. And I would have dy over g of y is equal to f of x dx. And now in order to get rid of these differentials, dy and dx on both sides of my equation, well, I could integrate on both sides. So on this left-hand side, I would have the integral of 1 over g of y dy is equal to the integral of f of x dx. So now, in general, we're working with these functions f of x and g of y, so we don't know exactly what these functions are, but let's say that we can find their antiderivatives. So on the left-hand side, let's say that the antiderivative of 1 over g of y is a function capital G of y, and in general, I could add some constant of integration. And on the right-hand side, let's say the antiderivative of f of x is capital F of x plus some other constant. Let's call it C2. So what I could do from here is group those constants of integration together. I could write this as g of y is equal to f of x plus c2 minus c1. Now, since c1 and c2 are arbitrary constants, those are any numbers that we could possibly want, any two constants, the difference, c2 minus c1, is just some new arbitrary constant. That is, the difference of two arbitrary numbers is just some new arbitrary number. So let's write this difference, c2 minus c1, as just some arbitrary constant c, in which case we would have g of y is equal to capital F of x plus some constant c. Now, in general, what we'd like to try to do for these separable equations is solve for y. So in some cases, we'll be able to solve for y pretty easily. In other cases, it will be very difficult or maybe impossible to solve for y. but we will try to solve for y and get our solution in explicit form. So here, if possible, we want our solution in explicit form, which means that we want a solution of the form y equals some function of x. But as I mentioned, this may not always be possible, and we may have to define our solution implicitly. So now that we've discussed sort of the general process for solving a separable equation, let's look at some examples of solving these separable equations. And later in this section, we'll start talking about some nice applications of these separable equations. So in our first example here, we are asked to solve the following equation. dy dx is x plus sine of x over 3y squared. And this is indeed a separable equation because we can think about this right-hand side as being factored as a function of x, namely x plus sine of x, times a function of y, 1 over 3y squared. So it is separable, and in order to solve this separable equation, we will first separate our variables. So if I want to get everything involving a y, let's say on the left-hand side of my equation, I could multiply both sides by 3y squared. And I would have 3y squared dy. And in order to get all of my x's on the right-hand side of my equation, I could multiply both sides by the differential of x. I would have x plus sine of x dx. So once we've separated or isolated our variables, x and y, we can then integrate on both sides. So I would be looking at the integral of 3y squared dy is equal to the integral of x plus sine of x dx. So now let's find our antiderivative on each side of this equation. The antiderivative of 3y squared is going to be y cubed. And on the right-hand side, the antiderivative of x plus sine x is 1/2 x squared minus cosine of x plus some constant c. Now we might ask at this stage, well, why didn't we include a constant on that left-hand side with the y cubed? And remember, we saw above that if you do include constants on both sides, say c1 and c2, you can always group them together and express this as a single constant on one side of your equation. So from this point forward, we will always group those constants on one side. So once we've found our antiderivatives, if possible, we'd like to try to solve for y explicitly. And in this case, to solve for y, we could take the cubed root of both sides, which would give us 1/2 x squared minus cosine of x plus some constant raised to the 1/3 power, or taking the cubed root of that function. So in this example, we have managed to solve for y. So this solution that we found is what is called an explicit solution. That is, we managed to solve for y. So let's look at a couple of other examples of this process of solving separable equations to illustrate some different things that we might run into. So in our next example, we are asked to solve the differential equation dy dx is equal to x squared times y. So we can see immediately that it is a separable equation. And in order to separate my variables, well, if I move all of my y's to the left-hand side, I could divide both sides by y. I would have dy over y. And if I multiply both sides by dx, I would have x squared times dx on this right-hand side. So once I've separated my variables, x and y, I can then integrate both sides. So I would be looking at the integral of 1 over y dy is equal to the integral of x squared dx, which then gives us a left-hand side of natural log absolute value y is equal to 1/3 x cubed plus some constant c. Again, I won't write constants on both sides of my equation because I could always group them together as a single constant on one side of my equation. So now from here, we'd like to try to solve for y explicitly if we can. And we see here that we need to get rid of this natural logarithm. So the inverse function for a natural logarithm is a base e exponential. So if I exponentiate both sides, I would have the absolute value of y is equal to e raised to the 1/3 x cubed plus c power. Now, one way that we could simplify this a little bit, so our solution currently looks a little bit messy, and we could clean this up by doing the following. We have the absolute value of y is equal to e raised to the x cubed over 3 plus c power, but using properties of exponential functions, I could rewrite this exponential where my exponent is a sum in terms of a product. So I could rewrite this as e to the x cubed over 3 times e to the c power, because I know if I were to multiply exponentials with the same base, well, I could take e and have my exponent as the sum of these exponents that I started with in the product. So here I'm just using that property in reverse. But now this e to the c term, since c is an arbitrary constant, is a new arbitrary constant. That is, e to the c is just some new constant. So let's call this constant e to the c just some new constant c. And now I have the absolute value of y is equal to some arbitrary constant times e to the x cubed over 3. And to get rid of this absolute value, we could make use of some properties from pre-calculus. I know if the absolute value of y is equal to this constant times e to the x cubed over 3, that means that the quantity inside the absolute value has to be positive or negative c times e to the x cubed over 3. But again here, whether I have the positive or the negative constant, since c is an arbitrary constant, it doesn't matter whether we have a positive or negative. The positive or negative of an arbitrary constant is just some new arbitrary constant. Let's call it c again. So we end up with y as a function of x is some constant c times e to the x cubed over 3 power. So this would be my general solution of this differential equation. So let's look at some other examples here. In our next example, part B of that same problem, we're asked to solve the following equation. And at first glance, it may not look like it's separable. But we can show that this equation is separable by factoring our denominator. So we notice that from the denominator, we can pull out a factor of x, and I'm left with y plus y cubed. And we can then think of this derivative as the product of a function of x, namely log x over x, and the product of a function of y, 1 over y plus y cubed. So we can see that this equation is indeed separable. And in order to solve a separable equation, we need to separate our variables and integrate. So again, if I move everything with the variable y to the left-hand side of my equation, I would have y plus y cubed dy. And if I move everything with an x to the right-hand side, I have the natural log of x over x times dx. So at this stage, we've separated our variables, and our next step is going to be to integrate both sides of this equation. So we have the integral of y plus y cubed dy is equal to the integral of natural log of x over x dx. So to get an antiderivative on this right-hand side, the left-hand side, we can apply the power rule, and we'll have 1/2 y squared plus 1/4 y to the fourth. And this is equal to, well, on this right-hand side, in order to integrate, we could make use of a u substitution. If we let u equal the natural log of x, then du is 1 over x dx. So then rewriting this right-hand side in terms of u, we have the integral of u, and the 1 over x dx is exactly equal to du. So we're left with just u du. And so we have 1/2 y squared plus 1/4 y to the fourth is equal to 1/2 of u squared plus some constant c. And u, in this example, was the natural log of x. So substituting u back in, we'll have the natural log of x quantity squared times 1/2 plus c for that right-hand side. So in this example, we see that it would not be very easy to solve for y explicitly. We have on this left-hand side a y squared and y to the fourth, and it's not very easy to solve a fourth degree equation in terms of y for y explicitly. So in this case, if it's not very easy or not possible to solve for y, we would leave our solution in this form as being defined implicitly by a relationship between x and y. Now, one thing that we could do to clean up our answer from here a little bit is to get rid of these messy fractional powers of 1/2, 1/4, and 1/2. So one way that I could get rid of those fractional coefficients is by multiplying everything through by 4, in which case I would have 2y squared plus y to the fourth is equal to 2 times the natural log of x quantity squared plus c. Now we might ask here, why is this term not 4 times c? Well, because 4 times an arbitrary constant is just a new arbitrary constant. So rather than call it 4c, I could just leave it as this constant c. So what we get is an equation relating x and y, which is not very easy to solve for y. So this would be an example of what is called an implicit solution for our differential equation. All right, so let's look at some other ones. In the next part of this example, we have dy dx is 6x squared divided by 2y plus cosine of y. So again, it's pretty easy to see that this is separable. We can think about this as being factored as 6x squared times 1 over 2y plus cosine of y, which is the product of a function of x and a function of y, so it is indeed separable. Now, to solve any separable equation, our first step is to separate the variables x and y. So if I were to multiply both sides by 2y plus cosine y, and multiply both sides by dx, I would have the following. 2y plus cosine y dy is equal to 6x squared dx. And once we separate our variables, our next step is to integrate on both sides. So we have 2y plus cosine of y dy is equal to the integral of 6x squared dx. And the antiderivative on this left-hand side is y squared plus sine of y. And this is equal to our antiderivative on the right. We would have 2x cubed plus some constant c. Again, I'm going to group all of my constants of integration on one side. Now here, again, we see that it would not be very easy to solve for y, because I see I have a y squared and y within the argument of sine. In this case, it's actually impossible to solve for y explicitly, so we would have to leave our solution in this implicit form again. So this is another example where we would have an implicit solution of our equation. So let's look at some other ones. In this next example, we are considering an initial value problem. So that is a differential equation together with some initial condition, y of 2 is equal to 0. And in part A of this example, we are asked to find the solution in explicit form. So we can see pretty quickly that this is indeed a separable differential equation. So my first step would be to separate the variables. And if we put everything with a y on the left-hand side, we would have 1 plus 2y times dy, and that would equal to 2x dx, putting all of our variables x on the right-hand side. So now integrating both sides, let's see what we have. The antiderivative of our function on the left would be y plus y squared, and this is equal to x squared plus some constant c. So at this stage, we could apply our initial condition. Our initial condition says that my solution curve has to pass through the point xy equals 2, 0. When x is equal to 2, we know that y must be 0. So applying this initial condition at this stage, let's see what we have. So the left-hand side, y plus y squared, if y is equal to 0, is simply 0. And this is equal to x squared. So if x is 2, we have 2 squared, or 4, plus some constant c, which implies that our constant c has to be -4. Now, if we take that constant, -4, and substitute back into the general solution we had earlier, we find y plus y squared is equal to x squared minus 4. Now, what we have is a solution to our differential equation, but the problem says that we need to express it in explicit form. That is, we need to solve for y. So one way that I could go about doing this is by rewriting my equation a little bit. we could rewrite this by moving all of our variables to one side of the equation, which would give us on our left-hand side y squared plus y minus x squared plus 4 is equal to 0. So I'm just going to move everything to one side of my equation. And we see that this equation is quadratic in terms of the variable y. It involves a y squared, a y, and then variables involving x, which are considered constant with respect to y. So in order to find the zeros, or the roots of any quadratic, we can make use of the quadratic formula. So here, the form of our solution would be y equals -1 plus or minus the square root of 1 squared, which is 1, minus 4 times 1 times a negative x squared plus 4, all over 2 times 1, or just 2. So simplifying a little bit, I have y is equal to -1 plus or minus the square root of. Now if we distribute these terms under the radical and combine like terms, we're left with a positive 4x squared, and then 1 minus 16 leaves us negative 15 all over 2. Now, we see here that we've actually got two solutions. One corresponding to the positive square root of 4x squared minus 15, and one corresponding to the negative square root of 4x squared minus 15. And we've got to be a little bit careful because only one of those solutions will satisfy our initial condition, y of 2 equals 0. So remember that the y coordinate for our solution has to pass through 0 at this point. So in order to pass through 0, we need to take the solution with a positive square root of 4x squared minus 15 over 2. If I took the negative value for that square root, my numerator would be -1 minus the square root of some quantity, which would be less than 0 always. It could never pass through 0, which is needed for our initial condition. So the reason that we're taking the positive square root here is since y of 2 has to be 0. We need to be able to pass through 0 here. So this would be our solution in explicit form. In this case, it was a little bit tricky, but we were able to solve for y making use of the quadratic formula. Now, in part B of this example, we're asked to determine the interval in which our solution is defined. So in part A, well, we just found our solution in explicit form, and in order for this solution to be defined, well, we have to be a little careful about what's under the square root. Here we have 4x squared minus 15 under the radical, and in order for this to be defined as a real number, we need this quantity, 4x squared minus 15, to be positive. Now you might say, well, shouldn't it be greater than or equal to 0? Because we could have the square root of 0 defined as 0, but let's think about what the problem is there. If the square root of 4x squared minus 15 were equal to 0, then we would find y is equal to -1/2. So it's defined as a real number. What's the problem? Well, in our differential equation, we had 1 plus 2y in our denominator. In order for this equation to be defined, we must have a non-zero denominator. It is not possible to take y equal to negative 1/2 in order for this equation to be defined. So we need strict inequality in part B. We need 4x squared minus 15 to be strictly positive. So let's go about solving for this inequality. This means that 4x squared would have to be strictly greater than 15. So x squared is greater than 15 over 4. And then taking the square root of x squared, I would have the absolute value of x is greater than the square root of 15 over 4, which reduces to the square root of 15 over 2. Now, in order for the absolute value of x to be greater than the square root of 15 over 2, that means that x would have to lie within the interval from negative infinity to negative square root of 15 over 2, or within the interval positive root 15 over 2 to positive infinity. Either I have negative values of x, which are less than negative root 15 over 2, or positive values of x that are greater than root 15 over 2. Now, for this initial value problem, our initial condition was y of 2 equals 0. So we're looking for the specific interval which contains the x value of positive 2, which means that we would have to be working with the positive interval. So here, since our initial value for x is positive, we must take the interval from positive root 15 over 2 to infinity. So in these first few examples that we've considered here, we're looking at how to solve separable differential equations by separating the variables and integrating on both sides. And we see that depending on the problem, we can find either an explicit or an implicit solution. And we can also have separable equations that maybe involve some initial condition, as in this last example. Now, in the next part of this section, we're going to discuss a few applications of separable differential equations in modeling, but I'd prefer to talk about those topics in a separate video from this one, so we'll discuss those modeling